how are we doing on resonance? We've covered most of this. Sort of the remainder that we've not covered is really for you to be working on your own. Application of resonance to acid-base chemistry. I think we did resonance structures of aniline. Yep. A neutral molecule has a lone pair that's conjugated in the pi system. When you have a lone pair that's conjugated, that's a great place to start with drawing your resonance structures. So there are two different things here, guys. The theory of the orbitals overlapping, the theory of the pi system. Understanding that structural theory that's there, the structural architecture. But then the other thing is just drawing resonance structures. And that's guided by your arrow movement. A couple of different ways, the old windshield wiper, the old in and out. Okay? Drawing resonance structures. But then what are the consequences of your resonance structures? All of your resonance structures make up your true structure, your hybrid, okay? Resonance hybrid. Then we can answer questions such as this here. We answered that one. The question is below here. I think it's, which amine is most electron rich? What's it say there? Which amino group is most electron rich? Basically, they both have a lone pair, but in each case, the lone pair is delocalized by resonance. You can move that lone pair around, and we can actually end up with a lone pair somewhere else. The more you can move it around, the more it's delocalized. The more it's delocalized, that means the less of the electrons are on the nitrogen. They're delocalized or moved somewhere else. Which amino group is most electron rich? Does that sound like it's the one where you can delocalize it the most or the least? Least. It's actually the least. Because the more you can delocalize it, the less electron rich the amine becomes, because you're moving the electrons away from it. Okay, so the remainder of this, I will send out sort of an answer key where I've worked these. All right. Anybody feel like they got the answer to this one here? Which amino group is most electron rich? Top or bottom? The difference between this and aniline is we got this extra group, this ketone group, which is conjugated. It's conjugated, right? P orbital, P orbital, P orbital, P orbital. So we got P orbitals all lined up here. There's no break in the chain here. P orbital, P orbital. With your resonance structures of aniline above, down here you may be able to draw extra resonance structures sort of into this group. Again, starting with the lone pair, great place to start. On one of the next examples, we'll see that this carbonyl is also a good place to start. You could start here and then work your way and end up moving here. Because this pi bond is polarized because of the oxygen. And polarity can help sort of guide our resonance structure drawing. We want to move the electrons towards the oxygen. I think we can look at that on the next page. That was A. Looking at the lone pair. Let's look at B. Acetone. 2 lone pairs on oxygen, right? How many electrons in the pi system here? Somebody? 2? Okay. Are you counting the lone pairs in that? No? Good. You should not. What type of orbital is the lone pairs in? Or are the lone pairs in? SP2? So are they in the pi system? No, only p orbitals. Pi electrons are in. Electrons are in p orbitals would be in the pi system. No, the electrons are not. These lone pairs are both in sp2. That's what we did back during week 1, week 2, understanding the architecture. So now that we get to this point, okay, it's just a pi bond, 2 electrons in the pi bond. Can we draw resonance here? Okay. Again, I see lots of students, not a lot, but some students trying to do resonance with these lone pairs. The lone pair is not in the p orbital, no resonance. Aniline on the previous page, the nitrogen lone pair is in a p orbital. Why? Because anytime a lone pair is next to a p orbital, it wants to be in a p orbital. We said that back in August. Okay? So what kind of resonance can you do here? Well, I just alluded to this on the previous page. On the first page, we had something like this, and we did a resonance structure. We moved these electrons here. Yeah? Look back on the first page. Did we do that? That was just a pi bond, and we sort of moved the electrons back onto one atom. Yeah? Did we get to something like that? And we had lone pair here that left us plus. Yeah? Just a pi bond. And we polarized it by moving the pi electrons onto there. But I said that this was not that intuitive because you don't have any polarity here. But here you do have polarity. It's a dipole here. And we can polarize this pi bond. Just like I move it to an atom, do you want to move the electrons to the oxygen or to the carbon? To the oxygen. The dipole tells you where the electrons need to go. So you have, it's more intuitive here. These electrons are being pulled by oxygen. Well, let's just go ahead and just move them all the way up there then. And what does that give? Now have 3 lone pairs on oxygen, and that's a minus charge, and the carbon is now plus. And we polarize the pi bond the direction it should be based on polarity, difference in electronegativity. But that over there is a resonance structure, because all we did is move pi electrons. And of course, this carbon is partial plus, and that's partial minus. We can see that from just the basic polarity considerations. But we can bring in the idea of resonance structures. And which one's major, left or right? Left, more bonds. Everything has an octet. If we had drawn this on day 1, we would have said, okay, carbon needs another bond. How do we get another bond? We would have moved these electrons down and got the pi bond. We would have went from one resonance structure to the other. And probably on week 1, I probably said at some point, that's actually a resonance structure in some cases. What's the true structure look like? What's the bond order between the C and the O? Is it 2 or is it 1? It's actually 1.5. What's the charge on the carbon? Is it plus or, let's get rid of that, or neutral? Partial plus. And on the oxygen? Partial minus. If you can look at acetone, it looks like, that's what it looks like over there. Well, then you got lone pairs. We can draw the lone pairs. But the bonding electrons sort of are sitting on the oxygen too. being pulled toward the oxygen. So sort of the dipole view and a resonance hybrid view. They say the same thing. See, this oxygen doesn't mind bonding to the carbon to help it out, but it likes to keep the electron density too. Again, these are fake structures. These are easy to work with because they're actual complete structures. Partial bonds get a little bit cumbersome to work with. It's actually the true thing, the true structure. Okay, so what did we just do there? Polarization of pi bonds to heteroatoms. Okay? Hopefully you understand that this is very important to read and understand and to guide your thinking as you try to understand what's going on here. Okay, show all possible resonance structures from the above cation. What type of resonance structure could you draw here? I should really clarify or expand this question and clarify it some. Probably going to see it said show all possible resonance structures that involve delocalization of the charge. Anybody have a resonance structure? What you got? Actually, no. Both of you have pretty much the same thing, unless I missed something. No, and you unfortunately broke one of the golden rules. Do we want to move these down like this and do... Pi bond here, single bond here. Yeah? How does that look? Isn't that what you did? No. You didn't break multiple rules. You only broke one rule. Unfortunately, I will see something like this on a quiz or test. It'll be like all of a sudden we go to a plus to a minus, and all of a sudden, there's actually two more electrons here. I don't know where they came from. Because there's only two lone pairs here. We move that down, how do we end up with a third up there? I don't know. Don't do that. Okay? Everything comes from your error movement. If you're going to move that down, you should know what that means at least. It means what? It means there's that up there. But what's the charge of this oxygen? Positive. It should be, because all resonance structures have the same net charge. What's the problem with that oxygen, though? What golden rule is that? Number 4. Should always have an octet. We said that last week, yeah? Very bad. This oxygen is going to hunt you down and make you pay for this. Is it a resonance structure? Sure, it's a resonance structure. All you did is move pi electrons. But it's so bad it ain't a good one. It's okay. It's no good. It's going to have no presence in the hybrid. The contribution of that to the hybrid is 0. No good. No octet. If this was an alkene, no oxygen, just carbon, we could do that. That's the old windshield wiper down, right? Boom, boom, boom. Here, and leave that as plus. Carbon is okay as plus. No octet. That's carbon. We see carbocations all the time. The golden rule didn't say anything about carbon. It said what? Heteroatoms that are more electronegative than carbon, mainly dealing with NO and halogens, should always have an octet. Okay? Yeah? Samuel? No good. Not a good resonance structure. Don't do that. Because the electrons are being pulled this way from just basic dipole considerations. Now I could just polarize the carbonyl and show like that. I would have these two charges generated. I'd still have a plus here. So that would not delocalize the charge. That's why I'm saying the question could be, what's a resonance structure that could delocalize the charge that's shown? There's only one, and it's right here. These electrons move in, and boom, boom. Yeah? Now the charge has been delocalized to the fluorine. And is that a good resonance structure? Does the fluorine have an octet? Yes, fluorine has an octet. If they have an octet, electronegative atoms are fine doing resonance. And actually, that's the major resonance structure, isn't it? More bonds. And every atom has an octet. That's the only resonance structure that involves delocalization of the charge. Again, you get that? I could have just polarized the pi bond like that, but then I would have had three charges, and that charge would have still been there. It would not have been delocalized. All right? Golden rule. Okay. Acidity, resonance structures. Most of this is going to be on the answer key I send you. You need to make sure you work through these. And before you look at the answer key, also look back at your acid-base handout from test 1 with some resonance there, yeah? These OH compounds, carboxylic acid, PKF4, phenol, 10, less acidic, regular alcohol, 16, even less acidic. Very important to understand this trend. Why is this one more acidic than that, and why is this more acidic than that? Very important fundamental understanding here. Like down here, it's a nitro group. Nitro group we'll see in organic 2. But it's coming off the ring, it's the nitrogen, and it double bond to one oxygen, single bond to the other. This oxygen is minus, the nitrogen is positive. Coming off the ring. This is your Lewis structure for your nitro group. Okay? 2 charges, you can't draw it without 2 charges, but it's net neutral. Okay? Nitro groups are very common, particularly on aromatic rings. Also a precursor to an NH2 group. But we can do resonance here. We have a pi bond. You can also do resonance of just a nitro group. You can move the pi bond here and move these out. The true structure of the nitro group is which NO bond is longer, top or bottom? Which one? They're the same. at C, the nitro group, both NO bonds with the same exact length. The two oxygens have the same exact electron density on them. But you're rarely going to, if ever, will see it drawn like this. You'll see it drawn like this, or just like that, but no structure. Okay. But we can take these electrons and move them in and move these out, and you end up with a double bond here and minus here. It's going to look just like this, but it's two equal contributors. Okay, you should be working those on your own. I'm not sure if these two are in the key I'm going to provide. If not, we'll look at these in class. Next time, I'll have to look at the key. Those two have been more recently added. Okay, the next handout chemistry of dienes. I know you've all been dying to all right, some warm up here. Dienes. Chapter 17. Yes.
Do you have extra?
I can.
Do you have extra?
Why don't you pass these around? Anybody need it here, Brad? Can you pass these back and pass them around there? Chemistry of dienes. What does a diene sound like? Di-2-ene alkene. Dienes. This is a diene. It's got two alkenes. All right? Now, we said alkynes are twice the fun. Well, these can also be twice the fun. Conjugated versus non-conjugated versus accumulated. That was on the resonance handout. Yeah? That was at the beginning of the resonance handout. Important terminology there. Nomenclature of dienes. We'll do that here. Longest continuous chain. The two enes, alkenes, must be in the longest continuous chain. Well, it's just one chain here. 1, 2, 3, 4, 5, 6, 7. Yeah? What is that? Heptane? What we do here is we replace the ane with heptadiene. So it's the prefix diene. If it was 4 carbons, it would be butadiene. 8 carbons, octadiene. Okay? So that's how we do this. If it was just one alkene, it would be heptene. So I reckon it's got the ADI added in here, keeping the A. All right. So heptadiene. Let's see. But we gotta know where the alkenes are at. What's the one in? Right or left?
Right.
Right. That would make the first alkene 2, and the next one would be 4. So we put in front here 2, 4 heptadiene. And the 2 and 4 indicate where both of the enes are. You got 2 enes, 2 and 4 position. It's 2,4 heptadiene. Well, what's the next compound? What's the next compound? It's also 2,4 heptadiene. It's a stereoisomer. What's the difference? No difference here. The difference is this alkene. This name is not clear. We have stereochemistry here. What's the stereochemistry of the first alkene? It's trans, but in terms of we're going to use EZ, the E. How about this one? Also E. What you would do here is we need to denote the stereochemistry E, comma E. This compound's stereogenic. It's got stereochemistry. We need to denote the stereochemistry with a stereochemical descriptor. Both double bonds are stereogenic. E, comma E. E goes with 2. The next indicator goes with the 4. Of course, they're the same. What do we have over here? This alkene is E, but this one is what?
Z.
It's cis. We're going to call that Z. It's the same side. That's 2. We list the Z, comma E. Same exact name. Z, comma E, 2,4-heptadiene. They have the same name, they just differ in stereochemical descriptors. They're stereoisomers. How about the third compound? How would you name it? What's the longest continuous chain?
6.
Not 8. Both alkenes need to be in the longest continuous chain. Both of them. 1, 2, 3, 4, 5, 6. Hexadiene, what's the one in, left or right?
Left. No, right. Right.
It can be right. Either way, it's a 1, 2, 3, 4. 1, comma 5 hexadiene. Either way, it's 1, 5. So how do we decide between 1, 5? That's just based on the alkenes. Now we can start looking at the substituents. If this is the 1 end, then the chlorine's at the 1, and the 1, 2, and the propyl's at the 2. 1 chloro, 2 propyl. One 5-hexadiene. And what stereochemistry do we have here? Chlorine here. Same. It's going to be high priority here, this carbon here. The opposite, yeah? E, 1 chloro, 2 propyl, 1 5-hexadiene. How does it look? And the E obviously goes with the stereogenic alkene. The other alkene is not stereogenic, right? So we don't need a descriptor for it. Okay, this guy here. What's that? 1, 2. What's the name of this compound? I don't know if it's written. It is written. 2-methyl, 1,3-butadiene. Yeah? That look right? 1,3-butadiene, methyl 2. Yeah. That compound is hugely important in nature. This compound is also known as isoprene. A common name, that's isoprene. Isoprene is a building block in nature, in many plants, to other organic compounds. Plants use isoprene to make other compounds. Where does the plant get the isoprene from? Home Depot. All right? Really, carbon dioxide. Don't plants take up carbon dioxide? That's the source of carbon. They turn carbon dioxide into that. Miraculous. But from that, they then make these other things. Where does the H's come from? Because ain't no H's in carbon dioxide. Water. Yeah. Make sure you water your plants. All right. Okay. Things that are made from isoprene are called terpenes. Terpenes are made from isoprene. And terpenes tend to be sort of polymeric products. This has a formula of C5H8. Many of your terpenes are just multiples of that, like C10H16 or C50H80 or something. It's just sort of dimers and trimers and tetramers of isoprene, different structures. All right. I showed you some of the formulas, like limonene. Where do you find limonene at? In lemons, yes, and other places. Beautiful structure, right? Yeah. Look at that. What is that? It's an exact dimer, right? Okay. I don't know. Some of these are not exact dimers because sometimes it may be a dimer, a trimer, and then elimination of water or something, or maybe water is added or something. Okay. Whenever it's not an exact dimer or trimer, instead of it being called a terpene, it's called a terpenoid. The terpenes are exact multiples of isoprene. If it's not an exact multiple, terpenoid. Because it still came from isoprene, one clue you can tell, anytime you see a natural product, see this methyl group hanging off? You see how lots of these methyl groups are sort of hanging off here? Methyl groups hanging off. That's sort of a clue that it came from isoprene. You'll maintain that. Heard of some of these? Squalene? Yeah? Fungal cell wall? Ever heard of squalene? A lot of antifungal medications inhibit the enzyme called squalene epoxidase. Keeping the fungus from epoxidizing squalene. Beta carotene, ever heard of it? Yeah, where do you find it at? How did the carrot make the beta carotene? Originally from isoprene, originally from CO2. Taxol, very important anti-cancer drug. Okay, so there are some terpenes. There was a class of natural products. Okay. There's a class of natural products we looked at during test 1 called alkaloids. What's the difference? Alkaloids had a basic nitrogen. Did any of those compounds have a basic nitrogen? No. So you wouldn't call them alkaloids. They're known as terpenes. Okay, let's look at some chemistry of dienes. 1,2 versus 1,4 addition. All right, we're going to look at very analogous chemistry we just were looking at with alkenes. Okay, alkene with HBr. Let's look at this first reaction. What's going on here? By the way, you look at the warm-up page and see sort of a little bit of intro to the cold temperature, warm temperature. What's going on here? How did we get this product here? This is an addition product. There's a new H on the end. H plus, Br minus, yeah? Looks like this reacted. Where are we going to leave cation, right or left? Correct, on the right. So we get new H on the end, yeah? Cation here. What do we need to do to get final product? Br minus just adds, right? Before we do that, though, what can we show here? Resonance. So resonance stabilized cation. Very important. The old windshield wiper, yeah? Resonance structure. But to get this product, Br minus just adds right here. And when it does, you get that product there. And that is the product if you do this reaction in cold temperature like minus 78, which is the temperature of dry ice and acetone. So it's not just a random temperature. This is called a 1,2 addition. The 1,2 indicates the relationship between where the H and the Br ends up. The H ends up here. There's a new H here, right? So the new H is there. The bromine is on which carbon? The next one, which would be 2. It's called a 1,2 addition. You'll see below 1,4. This is also called a direct addition because we're adding HBr directly to this alkene here, right here. It's almost like that we didn't even do anything over there. We didn't. We just added HBr directly to that alkene. Like I said, it's known as the kinetic product. Reactions of conjugated dienes, okay? It's a conjugated diene, and so the cation is actually conjugated. One thing to recognize there. Let's move down here, and I'm going to keep the same intermediate. The same intermediate is formed down here. If you do the same reaction at higher temperature, like about 40 degrees or higher, a little warming or higher, the same intermediate. Same intermediate as above. First off, which alkene are we going to react with? One left or right? Either one. It's the same. It's symmetrical. The alkene is symmetrical. Okay? If I had reacted over here, I would have made the same cation. It would have just been turned around. All right? How do we get to the same intermediate? It's the same reaction. I mean, it's the same. The only difference is going to be at the end. This attacks here, right? Swings out the cation here. It's the same exact reaction. So how do we get this product in, mechanistically? Instead of the Br minus adding here, it adds here, right? These electrons add here. What does that give? Gives that product. The only difference in these two reactions is at the last step where Br minus either adds here or here. higher temperature, it's going to end up adding as if it added out here. Now, as I say 1,2 addition, where's the new H at? New H is here. Because there's 2 here, now there's 3 here. So that's 1, where's the bromine? It's not at the 2 compared to that. This is not nomenclature, it's just that that's 1, the next one's 2. It's not there, where's it at? It's at the 4 compared to the 1. So we did what's called a 1,4 addition of HBr. And this is also not a direct addition. Did we directly add HBr to one of the alkenes? No, we did not do a direct addition. We did what's called a conjugate addition. Because the cation is conjugated, that's what allowed us to be able to add at the 4 carbon compared to the 1 carbon. We've been doing direct additions for the past month. This is our first conjugate or 1,4 addition. Question?
So can you explain why in this case the 1,4 is more stable than the 1?
Okay, it goes back to something we introduced about 4 weeks ago, and we actually marked the clock when we did it. And I said later on, we'll talk about it, and you guys won't remember. It was like about 8:20 one day. I can't remember exactly, but it's that reason. Very fundamental reason. Why is this product more stable than the above? They're both alkenes, and with alkenes we determine stability by substitution of the alkene. The alkene above is what type? Mono, di, tri? Mono substituted. The one below is what? Di. They're constitutional isomers. Which one's more stable? Di substituted. Right? Yes. So, you got di substituted. It's thermodynamically more stable. So of the 2, this is called the thermodynamic product. We're doing the same reaction, we're just doing a different temperature. If you do higher temperature, you're going to get which product? The thermodynamic product. Low temperature is going to give the kinetic product. What does kinetic mean? Kinetic is rate. That up there, that product's formed fastest. So it's called the kinetic product. It's not the most stable though. This is the most stable. We call that the kinetic. This is because it's going fastest. Okay, we have to figure out why. Why do you get a difference in these 2? We'll pick up there next time. Have a good day, guys.